Okay, we've introduced at a high level what generative adversarial networks and deep reinforcement learning are, gotten you excited about various applications, and we've also gone over installation instructions. There's one last prerequisite before we can actually dive into building our generative adversarial networks and our deep reinforcement learning algorithms, and that's just to make sure that we have the requisite theory background covered. So all of these concepts are covered in my Deep Learning with TensorFlow live lessons. So if you're in any doubt about what these terms are, pop into those and check it out. We spend several hours going over what each of these terms means, but I'll run over them quickly now as well, just to make sure that these concepts are fresh in the mind. So the underlying, the element, the atom of artificial neural networks, of deep learning architectures, is the artificial neuron. So there are 4 kinds of neurons that I talk about in my live lessons. The perceptron is overly simplistic. It only takes binary input and only gives binary output. So that was just used as an example to introduce artificial neurons. So I'm going to go ahead and scratch it out here. These other kinds of neurons, they do come in handy regularly. These are contemporary neurons that are useful to us. So sigmoid neurons, tangent neurons, and rectified linear units, they are types of activation functions that alter the output of a neuron before that information is passed along to neurons elsewhere in the network or to the output. The sigmoid neuron provides outputs on the range of 0 to 1. Tangent neurons provide output on the range of -1 to +1. And ReLU neurons provide output from 0 up to infinity, really, but in practice, typically the values end up being relatively close to 0. So tangent neurons and ReLU neurons, these are the ones that we see most often in the hidden layers of our neurons, and they are both very fast options. You're welcome to try either. Any place in these notebooks where I talk about rectified linear units, you're welcome to substitute with tanh and see what happens. Sigmoid neurons, we don't use quite as much. They tend not to train as fast as tanh or ReLU neurons, but they do sometimes pop up, for example, in output layers where we want the output to be from 0 to 1 on those particular bounds, like a probability output. There are 2 kinds of cost functions that I talk about across my live lessons. So cost functions provide us with an estimate of how correct or incorrect our algorithm is performing at a given instance. So after each iteration of training, we get an output from a cost function that says, hey, this is how far off you were on your outputs to the answer that was the correct answer. So one of the simpler cost functions to calculate is the quadratic cost, which is also called mean squared error cost. They're synonyms. And quadratic cost or mean squared error is it's a kind of cost function that, with the architecture of neural networks and these kind of other steps like gradient descent happening later on, typically a network will train slower with quadratic or mean squared error cost relative to with cross entropy cost. But in these live lessons, we will see an instance of using mean squared error anyway. So cross entropy, typically the cost function of choice, but we will be using quadratic cost once at least in these live lessons. So once we have an assessment of how wrong our network's performance is at any given instance with the cost function, then we use gradient descent to improve. So gradient descent uses partial derivative calculus to adjust the parameters, the weights and the biases within our artificial neural network based on where it was wrong, and it takes steps in the direction of the correct answer, so that as we pass more and more training data, we have more training iterations on our algorithm, the gradient descent algorithm gradually decreases cost, and our algorithm starts to give better and better answers. So the learning rate is the size of the step towards correctness. You can't really have a learning rate that's too small. The only problem with a slow learning rate is that it will take a long time for your network to train. The bigger error is to have a learning rate that is too high, so you take steps that are too big, because you will keep missing optimal answers. It can be the case that if your learning rate is far too large, then you will you won't be able to train at all. The mini batch size is the number of training cases that you consider in each gradient descent update. So this is called stochastic gradient descent when we do that. And the reason why we do that is that it's often computationally intractable to consider all of our training data at once. And also, depending on the application, smaller training data sets enable you to sample all of the possible spaces. You get samples of various costs, and that allows us to avoid getting stuck in a local minimum of cost, and it makes it easier to find the global minimum of cost. The final point related to gradient descent is that we typically will use second-order gradient descent algorithms. In my deep learning with TensorFlow Live lessons, we stuck with the Atom gradient descent optimizer. And the reason why we do this is that these take into account how quickly a given parameter, so a given weight or bias, has been learning over the recent training updates, and uses that information, that momentum information, to gradually adjust the learning rate. So that means that automatically, on a parameter by parameter basis, we can start with a fast learning rate. At the beginning of training, there's a high cost because we just started with random initialized weights and biases. And so this second order gradient descent starts by learning fast and gradually slows down as learning slows down. And that allows us to learn quickly in the beginning, but then gradually converge upon a great minimum cost overall. One point that's worth mentioning quickly is that it's the backpropagation algorithm that allows us to apply this kind of gradient descent throughout all the layers of our deep neural network. So that's just a term, backpropagation, that's worth mentioning here. Now, of course, deep neural networks, these models can be very large. They can have millions of parameters very easily. With Keras, you can, in a couple of lines of code, pump out a model with millions of parameters. But you might only have tens of thousands of data points, for example. And so in that kind of situation, it's very easy to overfit to your training set, and then your algorithm will not apply well to unseen data. So we need to take strategies to reduce overfitting. L1 or L2 regularization are well understood methodologies from machine learning in general. And so these penalize models for having parameters that are unnecessary. And so that's one option. Typically in my live lessons, including in these live lessons, we use dropout to reduce overfitting, where some proportion of the neurons are randomly removed. And so any individual neuron cannot become relied upon too much. And so this is a very effective strategy for reducing overfitting. The final one, if you can do it, is to expand your data set. So with some kind of visual stimulus, like the MNIST digits, you can rotate them slightly, and that gives you lots of extra data set, because a 3, if you twist it slightly, is still a 3. Or if you add noise to the image, it's still definitely a 3. So that's one option. With, say, the self-driving car example that I've talked about a number of times in these live lessons, you could expand your data set by collecting more footage, having more self-driving cars, collecting all of the possible information for training. Or some outfits actually use simulated data, so like Grand Theft Auto video game data to train their real-world driving algorithms. One thing that I mentioned a little bit earlier is that we need to initialize our network. So when we start training, we initialize with some random values, as all of our parameters in the network, all the weights and biases are randomly initialized. There are a lot of different options for doing that. You could not, for example, pick all zeros, because then there would be no variation within the network for the gradient descent algorithm to pick up on. So we have to start with some values, some non-zero values across our weights in the network. And in Keras, Glorot initialization is default. So although we won't be specifying this at any point in our networks, you can rest in the comfort that in behind Keras is specifying that TensorFlow should use Glorot initialization, which is an efficient way of initializing. Finally, let's talk about the layer types that are kind of assumed knowledge for these live lessons and that I introduced in my Deep Learning with TensorFlow live lessons. So the first is the dense layer, where all of the neurons in a given layer connect to all of the neurons in the next layer. These are a workhorse of deep learning, as I mentioned earlier in these live lessons, and we'll see these in most networks that we ever build. The softmax layer is used for the output layer. So if we have multiple classes, 10 classes of MNIST digits, then you use a softmax layer to get a probability from 0 to 1 that any given image is the digit 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. A max pooling layer is typically something that we use to reduce dimensionality. So we use the output from one neuron from a set of them, that neuron that has the most activity we use it as a proxy for all of the neurons in that area. So this reduces dimensionality and makes compute time faster, often with little downside. Flattened layers don't actually do any processing. They simply take a 3-dimensional or 2-dimensional input and convert it into a flat 1-dimensional array of outputs that can then be fed into typically a dense layer. So, convolutional layers often work on 2-dimensional or 3-dimensional data. We can pass those data into a flattened layer, which creates a 1-dimensional array that can then be passed into a dense layer. This is a very common use of the flattened layer. And I just mentioned the convolutional layer. It's our last point here, is that the convolutional layer allows us to identify spatial features. This is a beautiful complex operation that can identify features of an image or of natural language regardless of where that feature occurs in the image or in natural language. It's a very powerful tool, and we'll be seeing them a lot in these live lessons, particularly in the generative adversarial networks. All right, that brings our theory to a close. We're ready to get started with some new information.